Alright guys, so in the problem J-Hop gave us, we have 5 molecules and he wants us to find out if they're polar or non-polar. So the way you do that is you start off with the Lewis structure, then you go to the electron geometry of the molecule, and then you find the dipole movements and see if it's polar by that. I'll show you all in a minute. So to find the Lewis structure, I'm going to demonstrate with SO3. So you start off with S as the center molecule, or the center atom, because it's the least electronegative. You're going to have 3 O's because you have 3 in the molecule. This is how you find how many electrons you need in the total molecule of the Lewis structure. So we need 24. Each of the bonds count as 2. You're going to have 1, 2, 3, 4. Okay, so we're at this step. Now, this is violating the octet rule because it only has 6 electrons attached to it. So based on the rules of writing Lewis structures, we make a double bond to fill the valence of the center atom. Sulfur is on the 3rd row, so it can be a valence an octet rule breaker. This is the correct Lewis structure because all of the the formula charges are all 0. You get that by seeing the valence and subtracting 1 or 2 for each unbonded pair and 1 for each bond. So like O has 6. So you do minus 2, 4, minus 1, 2. So once they're all 0 if you count them up like that. So you want to get all the Lewis structures for all of them. Then you want to go ahead and do the electron geometry. This is trigonal planar, and it's the SO3 one. Because they're all at 120 degrees, they're all pulling at the same amount. It's going to be the double bonds here. Now you're going to have a dipole, which is whenever the electrons move from the center atom to the outside atoms. The O is more electronegative than the S. That's why it has a partial negative charge compared to a partial positive. Now, this means that the electrons are moved towards the O because it's electronegative, it wants the electrons. So since they all do that in the outside, like they all go in separate directions, 120 degrees, you're going to have no net dipole movement. And when they're equal and it's no movement net, it's going to be nonpolar. So you really want to do this with all of them. When you draw the OF2 molecule, fluorine's the most electronegative of all, so it's definitely going to have the partial negative charges. You're going to have 2 going down, so the net is a downward dipole movement. And since it's uneven, it's going to be polar. For BeCl2, you have the chlorines are more electronegative than Be, so they both go in opposite directions, making a linear electron geometry. Since they're both going in opposite directions, the movement cancels out. These 2 arrows cancel out, so it's going to be nonpolar. For CCl4, the electron geometry is tetrahedral. Now they're all going in opposite directions, but with the same magnitude of the arrows. The Cl is more electronegative than the carbons, so the dipole movement goes towards the Cls. Now it's hard to draw it on paper, but it basically looks like a tripod. It's going to have no net dipole movement, so it's going to be a nonpolar molecule. For the last one, the O3, this exhibits resonance. Now, since this one is more positive than these, the dipole movement goes downwards, and when you add them up, it gets to a polar molecule. Now, what's really going on in this molecule in a real life situation is that this double bond gets shared by each of these. Some common mistakes are creating double bonds where they aren't needed when doing the Lewis structure. Like I said earlier, these needed a double bond because the octet couldn't be filled. Another common mistake is not knowing which elements can violate the octet rule. All the elements from the third row and down can violate it by having more electrons. And some electrons, such as Be and boron, don't need all the electrons in its shell filled because they don't have enough electrons in the molecule. Alright, that's it for me. Signing out.